introduced to what this unit is called, matrices. And basically what a matrix is putting a bunch of numbers in a big set of square brackets. Doesn't sound very exciting, but is a rectangular array, in other words, square or rectangular box that holds numbers. You put the numbers in rows and you put the numbers in columns, and we call it a matrix. And it's used to organize data, right? We are going to find out that they simplify in some cases, maybe make it more complicated in other cases, the process of solving systems of equations. And all you're doing is writing the coefficients down instead of writing everything down. So they are a way to organize data, but cause us to write down less things, sort of like when we did synthetic division. You know how that organized things, but you didn't have to write as much? A matrix is similar to that. We call the horizontal entries the rows, and the vertical entries in columns. And we call a matrix by its size, and it has dimensions. So a 3 by 2 matrix would have 3 rows and 2 columns. Okay? I always remember this by just thinking that matrices rock. Rows first, then columns second, and you're fine. So here is a 3 by 4 matrix. This is what it would look like, just putting numbers in a rectangular box. We have 3 rows going horizontally, columns going up and down. You can think about columns on a building that go up and down to help you remember that a column goes up and down. And if you remember matrices rock, you say, well, how many rows are there? How many columns are there? And we call the 3 by 4 either the dimensions or the order. So, take a look at these 3 and write down the size or the order of them. And check how you did. We got a 3 by 1, 4 by 3, and 1 by 4. We usually use capital letters when we're talking about a matrix. So this was matrix M, matrix P, and matrix S. And we use little letters when we talk about the element or the number inside. Okay? I find it interesting in math that they keep coming up with different words for numbers. Right? What do you call the number all by itself in the end of a polynomial? Well, that's a constant. Right? And what do you call a number inside of a matrix? That's an element. They're just numbers. They're just different words as we're coming along. So what this would mean is if this was matrix A, 1, 2, 3, 4, 5, 6, we would call element 2, 3, and sometimes, I'll put it in blue, sometimes people write a comma there, and sometimes they don't. Because if there's 2 numbers written, it's sort of like, well, the first one's your row, the second one's your column. Element 2, 3 would equal, well, you would go to row 2, column 3. That's what that value is. So it's a way of defining where things are and describing, oh, which one are you looking for? That is the 2, 3 entry. That is the element in that spot. So here's an example of a whole bunch written in there. You've got this is called the main diagonal. That diagonal is going to come up important later on. So, taking that into consideration, write down the numbers for those three, and tell me the size of the matrix M. And how did you do? And the order, it has 3 rows, 4 columns. Some more matrix definitions. We call a column matrix a matrix with only one column. A row matrix has only one row. A square matrix is a square. Has the same amount of rows. Like you have to give them credit here in that when they made up their definitions, they made your life a lot easier, right? Someone could have got creative and said, oh, we're going to use different animals. So a column matrix we'll call a jaguar. And a row matrix we'll call a tiger matrix. And then you'd have a really tough time remembering them. But they went with common sense. Mathematicians tend to like to do that a fair bit so that it is easy. So these are all square matrices. This is a 1 by 1, which is also a row matrix, which is also a column matrix. This is a 2 by 2, a 3 by 3, and a 4 by 4. A zero matrix is if you put a whole bunch of zeros into any size of matrix, it's called a zero matrix if they're all zeros. Okay? It is denoted by a bold 0. So if you see a big dark 0, you're like, oh, that was a zero matrix. Okay? An identity matrix. Now, I don't know if you've heard the word identity in math before. Most of the time, you talk about the number 1. The number 1 is important in mathematics, especially for simplifying fractions and stuff, because we often multiply by 1 to not change the answer, but to change what it looks like. And so when you multiply by something that doesn't change what it does, it's called the identity. So there is an identity matrix, and we're going to find out with multiplication that when you multiply by this matrix, it doesn't change your answer. But what it looks like is 1s along the main diagonal and 0s everywhere else. So probably if you thought about multiplying by 1, if the 0 matrix was all zeros, you might have thought that the 1 matrix or the identity matrix would have all 1s, but it doesn't. It's just 1s along the main diagonal. And to use a capital I for your identity matrix, this is 2 by 2, this is 3 by 3. Identity matrix is always square as well. Okay, I guess. The last of our definitions is the transpose of a matrix. The transpose of a matrix is you decide to take the matrix you have and switch the rows with the columns. So what I could do with matrix A here is I could write its transpose. It was a 4 by 2. The transpose will be a 2 by 4. Row 1 was 4, 3, so that means column 1 becomes 4, 3. 2, -1, -1, 4, 5, and 7. And so what we've done is we have switched the rows and the column. Row 1 becomes column 1. Column 1 becomes row 1. And all a transpose is switching matrices. We are not going to use the transpose a ton, but it does come up in higher level math with matrices. Okay. So if you have matrices and you put numbers in boxes, well then you want to create some rules to do math. Our first math that we're going to do is adding and subtracting. And it is so easy. If you want to add or subtract matrices, you just add the corresponding elements that are in the same slot. So this means that you can only add matrices if they're the same size. Matrices that are different sizes cannot be added together. So here I have a 3 by 3 square matrix added to another 3 by 3 square matrix. And all we're going to do is add each individual spot and have to add 9 things to get our final answer. Is it hard? No. Not at all. Okay? Same thing with subtracting. Subtracting would be identical. You just subtract the individual same boxes. Here's another word for number. If you are multiplying a matrix by a number, we will call this scalar multiplication. So scalar is like another word for number in front. So if you had this 2 by 3 matrix, and there's a 2 out in front multiplying it, it means every single element in the matrix is going to get multiplied by 2. So it's sort of like distribution. 2 out in front, every single thing gets multiplied by 2. You're basically doubling the entire matrix. So far, matrix adding, subtracting, and multiplying by a scalar seems to match up with mathematics that we've done in other things. Okay, I will hand out 12A to you. Oh, that's fine. Continue from the video. We are going to find out how we can put these matrices into our graphing calculator. So what we do is we turn on our calculator and we find the matrix button, which on my calculator is in blue here, above the x to the -1. And in your matrix button, there are names of matrices. They give you A, B, C, D, E, F, G. Okay? You can do math with your matrices, and you can edit them. We're going to start with edit, and we are going to enter in matrix A, just as you see it here. It happens to be, how big is it? 2 rows by 3 columns. And we can go 1, 2, 3, 4, 5, 6. And we've entered in matrix A. We can go second matrix, go to edit, and put in, second matrix, go to edit, and we edit matrix B now. And matrix B is a 3 by 2 with, well, not a 32 by 2, 3 by 2, and 1, 0, So the first thing we're going to do is we are going to put all of these matrices into our calculator. The next thing we're going to do is if you're in your regular screen and once you've entered them all, we're going to do the math. We're going to see what happens if you do A times B. So the way that you write A times B in your calculator, you're going to go to your matrix button, you're going to pick A and push enter and A appears. And then you hit your times button and go to second matrix and go to your matrix B, which is there, push enter. And then push enter and write down your answer. And it's really obvious that this times this would be that. What is going on? We have no idea. That's part of the fun for the rest of the class today. First of all, we're going to multiply all of these, and you're going to find out that sometimes multiplication works, and sometimes it doesn't. When does it work? Puzzle number one. When does it work? And when doesn't it? I can tell by looking at D times B that it's going to work. And I can tell you how big my answer is going to be. Like, for example, this one was a 2 by 2 in the end. This one, when you type it in, is going to end up being a 3 by 2. Okay, how do I know that? How do I know that even though I could do A times B, that, oh yeah, I can do B times A, but I can't do B times D, even though I could do B times B. That's weird. D times B exists, but B times D is not possible. What? Matrix multiplication is a little messed up. That's going to be our job. Without cheating and reading ahead, right, to see if you can figure out the patterns, why some things work and why they do not. So, first of all, you have them typed into your calculator. Write down the answers for the following. A times B, we've got D times B. I want you to do C squared, E times B, B times A, and A squared. Find out those answers. And then we're going to try and figure out how this works. So I've given a hint to say, looking at the dimensions might say when something works and when something doesn't. So if we look here, I've got E times B. And I'm looking at that one because that one's 16 and 10. That seems like the smallest answer. So maybe it would help us figure out things the most. E is a 1 by 3. and B was a 3 by 2. And you're allowed to multiply those together. So there's something that works in that one that allows you to multiply. Oh, I don't want to go to the allows you. You saw it, right? I was so annoyed that you didn't see. There's something that allows you to multiply those. So let's look at the ones that worked. Let's look at A's size. A was a 2 by, oops, right there. Right about A. A was a 2 by 3, and B was a 3 by 2, and the answer is a 2 by 2. D is a 3 by 3. B is a 3 by 2, and the answer was a 3 by 2. And here we have a 1 by 3 times a 3 by 2, and the answer is a 1 by 2. And B was a 3 by 2, and A is a 2 by 3, and the answer is a 3 by 3. But the ones that don't work, you can't do a 2 by 3 multiplied by, 3 by 2. B is a 3 by 2, cannot multiply that by a 3 by 3. And A, which was a 2 by 3, cannot multiply by itself another 2 by 3. So what do the ones that work have in common that the ones that don't work have? Right? Especially like, why did, like, A times B and B times A both work, but D times B and B times D doesn't?
Because it should be, for example, 2 by 3 or 3 by 2, but one of them can be 3 by 3 and 2 by 3.
So what, yeah, okay, maybe, but what would be the succinct thing that you see that makes it work? What do you see else?
The columns of the first have to be the same as the rows of the second.
All right, so the columns of the first one, which is this number, and the rows of the second one, let's be circling all the middle numbers. Look what happened here. They're different. Look what happened here. They're different. So if the middle numbers match up, in other words, if the columns of the first one match up with the rows of the second one, then you're allowed to multiply. C is if you do look at C, C was a 2 by 2, and by another 2 by 2, my middle numbers match up. So those middle dimensions have to match up in order to be allowed to multiply. Rule number 1. Rule number 2, can you figure out that, for example, I'm going to make up a 2 by 4, and I'm going to multiply it by a 4 by 3. Can you see that that would be allowed? Because these middle numbers are the same. How big is my answer? You see the pattern that in the size of the answer.
It's 2 by 3.
2 by 3? You are right. It will be a 2 by 3. So now we have at least figured out when you're allowed to do it, how big your answer is. But now, how do you get 16? How do you get 10? Isn't it obvious? No.
We should just change.
second hint. 16 is in row 1, column 1. Its position would be little f 1, 1. It's in row 1, column 1. 16 is related to row 1 of your first matrix and column 1 of your second matrix. Somehow. And whichever way you can figure out to get a 16 with row 1 and column 1, you have to use that same strategy to get a 10 with row 1, column 2. Now, as a starting point, can you see in row 1 and column 2, there's a 5 and a 2, and that, if you multiply, makes 10. And it's sort of like, I feel that worked. But that would just be me multiplying this 5 times that 2,
But you also,
and got 10.
but we can say we multiply 5 by 2 zeros, and
So you just take, if you just took the last one and multiplied them all,
yeah,
you get 10.
yeah.
But that doesn't work for the 1, because 1, if you multiply them all, I would only get 3. It's weird. What do you see?
Like if you multiply them like in order, so like the first one from like E and the first one from B, and then you like keep going in order.
So you multiply this one,
Yeah.
this one, and this one,
And you add them.
and then you add them. Does that give you 16? And does it work if I multiply this one? Okay. It works. Let's see if it works for, let's go to the A times B. Let's see if you take row 1 and column 1, do you get 8? Using that strategy. So what she's saying is I take the first one by the first one, the second by the second, the third by the third, and add them up. It happens to work here. Sometimes we find something that works in one spot, but does it work in this one? So like if you wanted to find the 17 is in row 2, column 1. So you'd have to take row 2 and column 1, and does it work?
Maybe we should do the column 2.
Well, row 2 and column 2, it should give you the 12. Does it work?
Well, the first one is what? The 8.
For 8 it works. Yes.
What is it? 17. So yeah, so for 17 is row 2. And for the 6, it's row 2. You're a genius.
Maria is now
Yeah,
reached
it's
Roham genius.
yeah, it's worked for all of us.
Isn't that messed up as a multiplication technique? It's like, this is how we're going to add, and you're like, this is good. And this is how we're going to multiply. And there's a reason for it. Okay? We will eventually do an application, some applications to matrix multiplication, and it will make sense why we do it this way. But right now, it seems like the weirdest rule in the world. So if I multiply corresponding ones, 1 times 1, that's 1. 2 times -1, that's -2. and 3 times 3, that's 9. And I add them together, I get 8. That's our first number. Right? If I wanted to do, let's look at here, this 3 by 3 one. Let's pick a random number. Let's choose the 16 in the B times A. That 16 is in row 3, column 2. So I would take row 3 from B, column 2 from A. 3 times 2 is 6. 2 times 5 is 10. Add them together and get 16. So matrix multiplication is a combination of multiplying and adding. And I sort of like the following visual here. Let me erase my arrows here. I sort of imagine that this row gets rotated on its side, like that, and then crashes into the column straight across. So what happens when it crashes? The 1 multiplies into 1, the 0 multiplies into the -1, the 5 multiplies into 3. And because it's the crash, you got to pick up the pieces afterwards, so you just add up whatever's left as a visual for what's happening in matrix multiplication. So the first one is first it turns and crashes into that column, then it turns and crashes into the second column. And every row crashes into every column from one matrix to the other matrix. Pick up the pieces and see what you have as an answer.